I am going to skip past them, yeah. So I do have a few things here on the wave packets, but yeah, I'm also skipping past the Heisenberg uncertainty calculation, so I'm going to start here. So let's look at what we have learned so far about quantum mechanics. So we started just with formalisms, right? And so that was learning how to normalize and how we use operators and that kind of thing. And then we looked at, in this chapter, the solutions we got when we had finite or infinite barriers. So I have the infinite square wall, particle in the box problem. And with that, we had stationary states. We had specific energies. This energy, or this energy. And the harmonic oscillator, likewise. It was bound and it had specific energy levels. So what we can see from that, if we boldly extrapolate from the example of 2, if we have boundaries, we'll have quantization. When we had the free particle, it wasn't quantized. We have that K value in there that tells you about the energy, but there are lots of energies. And if you read through the textbook, you see that we say, well, now since we have continuous, we have to integrate our energy state with our continuous solutions to find a specific energy. But it's not physically possible because you can't normalize it. Now, one thing that you can do with that is what the topic of today's lecture would have been, is you can shift from being in position space to phase space, and you can normalize the phase space solutions. But one of the important things here, what I want you to know, is that if you have something that's a free particle, you have continuous states, and it's not normalizable. So that's not what we're going to focus on for quantum mechanics. It's when they're bound, then it's normalizable, and you have specific indexed energies. And so moving forward from there, we've learned previously about the Kronecker delta. So Kronecker delta, it's a delta, so we have the Greek letter delta. But Greek letter delta. It had subscripts like n comma m. Oops. I put those in the wrong order and put the wrong value initially. It equals 0 if n is not equal to m, or 1 if n equals m. That was our Kronecker delta. Now we have the Dirac delta. So the Dirac delta is still a delta function, so it's still written as a delta, but the Dirac delta is written here. And so you have the Dirac delta is delta as a function of a variable instead of delta with 2 subscripts. But it still has the same fundamental meaning of it's 0 or 1. It's 0 if the variable is not 0. And it's 1 if the variable is 0. And I say 1. You see up there it says infinity, right? But the important thing is it has an area of 1. If you integrate the Dirac delta, what you get is the result of the integral is the value of your function at that value of x. So there's different functions people will come up with depending on their problem. They'll use actually a different physical function for Dirac delta. So the important thing is the integral from minus infinity to infinity of the Dirac delta dx is 1. And it's 0 at every location except when x equals 0. So this is vital. But since it's 0 everywhere except where x equals 0, there's actually some meaning there. It's not just, oh, it's infinite. You know, the textbook says don't worry about it. The important thing is that you have this integral as 1. So rubber meets the road. Like I said, the integral of f of x can be done instantly without any thought, because the Dirac delta is going to be 0 for all values except when x minus a is 0. So when x is equal to a is the only time when this is not a 0. And then this Dirac delta, the integral is going to give you a 1. So it's just going to be 1 times the function at x equals a. And so the solution of that, like I said, without thought, is just the function at a. So it's a useful idea, and it's one that we're going to be using right here today. So have you guys seen this Dirac delta function before? New? Okay, then I'm glad I defined it a little more carefully instead of just said, and we have the Dirac delta and moved on. What we're going to do with this is we're going to say, what if I have a potential well that is a Dirac delta function? So it's kind of like the same thing as a free particle, except for my potential energy is 0 everywhere except for at x equals 0. And at x equals 0, my potential energy drops to negative alpha. So I put that in my Schrodinger equation. So here's the Schrodinger equation. Then I want to find the solutions. Well, let's go back and apply the techniques we learned for the particle in the box. So what do you remember for how we started finding the solution to the Schrodinger equation for the particle in the box?
It was a long process.
It was a long process. That's true.
We talked about the boundary conditions.
Okay.
First, there's like potential energy and then boundary conditions.
Now we applied boundary conditions after we had found a solution to the Schrodinger equation.
Right. So we used the potential energy function to find the solution to the
Okay.
Schrodinger equation.
But there's a step in there that's vital to remember. We broke up our region when we had the particle in the box. We broke it up. Those are infinities. We broke it up into regions 1, 2, and 3. And we found a solution in each one of those regions. So we're going to do the same technique here, right? Same process, but a different potential. So now if I draw this potential goes like that. So how many regions do I have here? 2. So I'm going to call them my left region and my right region. Seems good enough. So now that I have 2 regions, I'm going to go ahead and solve the Schrodinger equation. So what's my Schrodinger equation? Well, what is my potential in the left region? What was the potential energy function everywhere where x was not equal to 0? 0. So potential energy is 0 there, and potential energy right is also 0. So obviously the work I do on the left side, I can do on the right side because it's the same potential energy. So for both of those, and I've taken to writing bigger, I believe. Insert a page or 2. I'm going to insert 2 pages just to be sure I have enough space. So now I'm going to take the left region. That's going from minus infinity to 0. And I have that. I put the 0 in there explicitly. Obviously, you don't need to put that in there because it's just 0. At this point, you should be able to recall what is the form of psi that is the solution to this. And so taking the second derivative of that, I'm going to have minus h bar squared over 2m b squared psi equals e psi. Or this. So this will be true if psi is 0. We immediately throw that away because that's the trivial solution. That is, we don't have an actual particle. So we throw that away, and then we say, okay, throwing that away, then I have this thing in parentheses must be 0. So b squared must be equal to minus 2me over h bar squared. Yeah. So what does that give you for b?
Plus or minus IK.
Now, we didn't say anything about the energy. The energy could be positive or the energy could be negative. In the free particle, the energy was always positive because there's no potential energy. But here, we have a potential energy, and we could have a negative energy because of the negative potential energy. And so we actually have the option of a negative or a positive. So we have to consider the two options. If energy is greater than 0, then K is equal to square root 2me over h bar squared, and psi is equal to ae to the ikx plus be to the minus ikx, right? That's the free particle solution. But we also have, if E is less than 0, then we don't have a square root of a negative value. And so I'm going to, I think the textbook uses kappa. Let me check what the textbook uses. I don't like to use kappa because it really makes life difficult. Where is it? Yeah, the textbook uses kappa. I'm not going to use kappa here because my kappas and k's look way too much alike. So I am going to use L. The difference is I versus no I. Why do I have two solutions in both cases, an A and a B in the top one or a C and a D in the bottom one?
Because you can have a positive or negative solution to each of
Right. It's the plus and minus right here that results in me having the two. And the difference in having the I and not having the I is if the thing inside the square root is positive or negative.
So you just pulled out another I from that L term?
No, there's no I because E is negative, so minus and negative is positive. Right, so we have two different types of solutions. Now let's describe these. What would you call the description for the case where energy is greater than 0? hint yesterday.
Sinusoids?
Okay, there's sinusoids, but we would call that a free particle. That's the solution for a free particle. You have one of those waves is going to be traveling forward, one of them is going to be traveling backward. Right? We worked through that yesterday, and it turns out because we have e to the minus I e over h bar t, the one with the positive exponent here is going to the right, the one with the negative exponent is going to the left. So this is a left and a right going wave for a free particle. Now remember, it's the same solution on both sides up to this point. And so if we have a positive energy, let's just go back to the picture. Now I'm going to take this picture and I'm going to modify it a little bit. I'm going to give it some measurable, or some visible, obviously there is no measurable. I'm going to give it some visible width. We know in reality it has no visible width because it's a delta function. But I'm going to give it some visible width. In the case where energy is positive, my energy level is up here. What does it care that there is this divot down here? Right? It's flying right over. But it does make a difference. We say that it scatters. So we have scattering states here. Because, well, let's think about something that's easier to imagine. You have an asteroid that passes by the Earth. And as it passes by the Earth, if it has a positive energy, it's going to keep going. It's not going to hit the Earth unless it's on a collision course. Right? If it passes like this, it's not going to hit the Earth. But is it just going to go undeviated? Because of the Earth's potential energy, it's going to actually have a change in its path. It's going to be scattered by the Earth's potential energy. Yes, gravity. The potential energy associated with the Earth's gravity. I should be really clear on that. So we're going to have a similar thing here. This energy well is very much like if I have an asteroid passing by the Earth, it comes by and all of a sudden it sees the Earth's energy. You know, the potential energy from this is no longer zero, it becomes negative, and it makes it change somehow. So we call that scattering, that interaction. But it's not going to be trapped by the Earth if it's coming fast enough.
So is the particle what's moving and the well is what's scattering it? Or?
Yes. So we have a left and a right going wave, and then that left and right going wave is going to be scattered by hitting this. So we're going to have some kind of interaction that occurs here. And the textbook goes into, we have the solution on the right-hand side is going to look the same. And so you have a left going and a right going wave on the left side, a left going and right going wave on the right side, and then you use your boundary conditions to find how those relate. I'm not going to do that because we didn't spend enough time on the scattering states, I don't think, to make it sensical for us. What I am going to do is take the states where the energy is negative. If the energy is negative, here's the energy level. Now let's be realistic. If this was real, if the energy level is here, in classical physics, we don't have enough energy to climb any higher. And so that particle is going to be stuck in that little region, right? That's what classical physics would say. But quantum physics gives you a different answer. Quantum physics says it doesn't have enough energy to be outside of that little well, but there's a probability that it's outside of that well. And so we're going to look at the actual answer quantum physics gives us for this situation. So, going to our solutions for energy is less than zero. I'm going to have psi left is equal to C e to the Lx plus D e to the minus Lx, and psi right equals F e to the Lx plus g e to the minus lx. Now we can simplify this immediately. You know, somebody watching the video might be saying, why did he write it like that? Is he crazy? What can you see how I can drop half of the terms that I just wrote?
Well, with the particle box we used
We did. That was for the sinusoidal ones, the either minus ikx or plus ikx. Our solutions to the Schrodinger equation have to be, this is something you said I should put on the test for you. They have to be normalizable.
So you can drop off the ones that go to infinity.
I can drop off the ones that go to infinity. So the left-hand side, I'm going from x equals minus infinity to 0. Now at 0, both of these are just e to the 0, 1. So there's no blowing up at 0. That's not a problem. But at minus infinity, one of these blows up. Which one blows up? D. So that means D is going to have to be 0 for it to be something we can normalize. Because e to the minus lx will blow up at minus infinity. The question, why? Okay, so e to the minus l times minus infinity, right? That's the value as you approach x equals minus infinity. That's equal to e to the plus L infinity. E to the infinity is infinite. And so if your function is infinite, you can't normalize it. It has to approach 0 at x approaches infinity or minus infinity for it to be normalized. So D has to be 0. What about on the right side? Not G. Because on the right side, we're going from x equals 0 to plus infinity. And so when x is plus infinity, which one of these two terms is blowing up? The one with f. And so f is going to have to be 0 for that one to be something we can normalize. So we already have cut out 2 of our 4 constants. And all God's children said, amen, right? Making life easier. So it is a boundary condition. It's never listed as a boundary condition. To be normalizable, you have to have it approach 0 plus or minus infinity. So now we have psi left is equal to ce to the lx, and psi right equals ge to the minus lx. And then we apply our boundary condition. Psi left at x equals 0 must equal psi right at x equals 0. So that means c e to the 0 must equal g e to the 0. Yay! C must equal g. So I have psi left is equal to c e to the lx, and psi right equals c e to the minus lx. Well, we've come a long way. We can now draw what this looks like. And we can normalize it. So if I draw this, it can't hit 0, so I'm going to redraw that. It should be symmetric, like that. And then if I normalize it, integral from minus infinity to plus infinity of psi star psi dx is equal to integral from minus infinity to 0 of psi left mod squared dx plus integral from 0 to infinity of psi right mod squared dx. Why do I have the 2 different integrals? Okay, I had psi left only applied from minus infinity to 0. Psi right only applied from 0 to plus infinity. So now I can go ahead and put in my function. I'll be explicit. C star e to the minus Lx times C e to the minus Lx dx. To the plus. Did that wrong. This one was the plus. I made a mistake on the previous page. I didn't pay attention to the signs. So I got to go back. I think I wrote, oh no, I did have the signs right. Right, you have to have the positive exponent for the left side and the negative exponent for the right side. So here, if I do the integral, I'm going to have C mod squared times the integral of e to the 2Lx so there's my integrals. C mod squared times integral of e to the 2Lx. It's going to be divide by the derivative of the exponent. Derivative of the exponent is 2L. And then the e to the 2Lx again. The second one, you're dividing by minus 2L. So I'll put minus. Nope, can't have them with the same limits because they're different limits. So there I have the two integrals. I will divide by the 2L out here. And I'm going to have, putting in the 0 limit, I have e to the 0 is 1 minus putting in minus infinity for the limit, e to the minus infinity is 0. So that is my first brackets minus the second brackets, putting infinity, e to the minus infinity is 0 minus, and then e to the 0 is 1. 1 minus 0 minus, and minus 1 is 2. So this whole thing in parentheses is just 2. So it's equal to C mod squared over L. Well, this was normalizing. What is this normalization integral supposed to equal? 1. Therefore, C is equal to, well, instead of putting plus or minus, I'm going to be all kinds of. The e to the I phi just represents it could have any phase and could be complex with any, we'll just drop C is square root L solution. Easy solution, so we're going to go with that. So we have our normalization constant. I don't think I made a mistake there. So now we have a normalized wave function. We have solved the Schrodinger equation. Yippee skippy. What good does it do me? We haven't quantized anything yet, have we? No, we haven't quantized anything, but we have a solution, and it's normalized. So I could go and put it into my Schrodinger equation, but we actually know it's just going to give us energy is energy. So we got to do something more. Okay, we've already done this. We've already done this. Notice I have kappa because I wanted to be consistent with the textbook. We used L here to make our lives easy. And so B and F, we had C and G. Doesn't matter. There's a graph showing what it looks like. We used our boundary condition. We found C was equal to G, so we just used C. And now we have the second boundary condition, the one that is normally that the derivative of the wave function is constant. Here's where it comes from, and here's how it's going to be different when you have an infinite potential. So if we just take our Schrodinger equation, right, here's our Schrodinger equation, and we integrate it. Now, I got to be honest with you. I am unlikely to think, oh, yes, I'm going to try to integrate that Schrodinger equation. It's just not what I tend to think. But if we integrate that, the reason we're doing this is because we are going to have right here the integral of v psi. So let's do that one first. Let's do that one first because that's the one that we're learning the first time today. So, by the way, notice this whole, the minus h bar squared over 2m, both sides were divided by minus h bar squared over 2m. And this term was moved over to here, so it was subtracted. So if we subtract, it's going to be minus and then when you divide by minus h bar squared over 2m, that becomes a plus. So that's, I just want to make sure it's clear where we got those terms that look different in the second equation. So if I do this integral, so I have 2m over h bar squared, integral minus epsilon to epsilon. I can't write it that close because you can't see one color on top of the other. And I should point out the limits of integration are minus epsilon to plus epsilon, where epsilon is a very small value. So we're integrating this, but we're not integrating from minus infinity to plus infinity. We're integrating from just one side of the potential spike to the other side of the potential spike. And when we do this, when I do this integral, what do I get for the integral of the Dirac delta times psi?
Is this a case where x equals 0?
Well, because we're symmetric about 0, we're going through 0, yes. So what was the rule? Going back a few slides, I'll go back to the rule. More than a few. One more. Integral of some function times a delta. Instead of delta x minus a, it's delta x. What does that give us? The value of the function at the location where the argument of delta is 0. So since I have delta x, then it's going to be the function of 0, because it's when x is 0. So going to this integral, hopefully I don't sneeze here. Went too far. this is equal to, excuse me, don't forget the 2m over h bar squared, and don't forget the minus alpha. And then I have psi of 0. Well, given that our psi I'm going to put C here. Both of those at x equals 0 are equal to C. Then I have this is equal to 2m over h bar squared times minus alpha times that C, the normalization constant that we found, which I think was square root of L, right? So that's what that integral is. Now we look at the other integrals. The integral of E, well, E was a constant, right? Because E is going to be fixed. And so we just have integral of psi going from minus epsilon to plus epsilon. Well, how much is psi going to change? We had a rule. Psi has to be continuous. So that means for some infinitesimal switch, the change in psi is 0. So this integral is going to be the change in psi is 0. Psi is constant. Well, I know I have in slides coming up, but I want to do it here, and suddenly I've lost my confidence. Let's go to the front term and do that one because I still have confidence on that one. The front term, the limit as epsilon approaches 0 of, if we take the integral of a derivative, and of course the second derivative is the derivative of the first derivative. So if we take the integral of a derivative, then we just get the original function. So if we take the integral of the second derivative, we obviously get the first derivative. And so we have the difference in the first derivative on one side of our boundary and on the other side of the boundary. And so what we have there is going to be, if we take the left side, well, see on plus epsilon, that's going to be the right side, right? And it's going to be the left side for the minus. And so if we take those, the derivative on the left side is going to bring down an L. The derivative on the right side is going to bring down a minus L. And so this one here, the limit as epsilon approaches 0 of the integral of d second psi dx squared from minus epsilon to epsilon dx is equal to what is written right there. And so putting in those derivatives, the left side is going to be C e to the L epsilon, bring down L, times L, minus the derivative, wait, right side is bring down a minus L. Then the left side is bring down a plus L. So there I've put in the derivatives. And since epsilon is approaching 0, then this e to the 0 is 1. This e to the 0 is 1. And so that's equal to minus 2LC, or minus 2L to the 3/2 power, assuming that I did the normalization right.
So why did you not put in a negative epsilon for the left-hand side?
Well,
I mean
okay. Psi left has a positive exponent. And so when I did the derivative of psi left, I had a positive exponent, and so I brought down a positive L.
Okay, and then when you multiply.
And then the right, I brought down a negative L, and I had a negative exponent. But in both cases, when I put in epsilon, when I evaluate, I'm putting in 0 because epsilon's approaching 0.
Oh, okay.
So that's that first integral. And the last one is 0, I'm pretty sure. Yeah, unless v is infinite, then the right side is 0. Because you take the integral over 0 space and you have nothing. Right? It doesn't matter what your function is unless it's infinite. If you take some finite height times a width that's approaching 0, you have 0. And so this integral here is going to give us 0. And so what we're left with is an equation that says minus 2L to the 3/2 power is equal to minus 2m alpha over h bar squared times the square root of L, or L to the 1/2 power. Notice I had that C value on both sides. It didn't matter if I'd normalized correctly or not. I would still get the same result here, which then says that L is equal to m alpha over h bar squared. Now, what is useful about knowing L? We had defined L was equal to the square root of minus 2me over h bar squared. And so now that I have L, I can now solve for E. So I have this on the following slide here. Notice I had alpha instead of L, but the end result was that, yeah, L equaled m alpha over h bar, right? Or h bar squared, yeah. Just making sure I have the same result. We had called this L on our slide, or on our work. And so putting that into our equation, then if I square, I'm going to have equal to m squared alpha squared over h bar to the 4th equals minus 2me over h bar squared. And so if I solve that for E, I have E is equal to minus h bar squared L squared over 2m equals minus m alpha squared over 2h bar squared. Now here's something to ponder. Is this quantized?
What was alpha again?
Alpha was a parameter given to us. It was the depth of the potential energy spike. So it's a single value. Is this quantized? The answer is it is quantized. It is quantized because it has only specific energy value. Ooh, yes. It only has one possible energy. It's quantized with only one energy you can have. So the particle can't have this energy, that energy, or another. If the particle exists and you have a negative energy, you have to have that energy. So, oh goodness. Time she flies when we're having fun. So this is the solution for a single Dirac delta well. And this is the solution for a bound state. Now, scattering states, that's a different problem that, like I said, we're not going to work on today. Now I have the let's normalize, and you see that I did do my normalization calculation correctly. I had square root L kappa L. So here is the positive energy one that I'm not going to do. It becomes crazy. You have the solutions for your boundary conditions. Notice you can't say A equals 0 or B equals 0 because for the sinusoid, it's just continuing. Now you have the problem of, I can't normalize this, right? That's kind of a problem. But we can still do other quantum physics. So we can get our boundary condition at x equals 0, that they have to be the same. And so we have A plus B equals F plus G. And then the slopes, the difference in the slope has to be minus 2, the alpha, because the potential energy had the alpha, m over h bar squared. So this here, that comes from the same derivation that we had for doing this calculation here. Right, this, well, I can just stop here. Right, how we found that difference. And so, actually, no, I do. We had to combine these two. Now I think about it, yeah. We had to combine those two. But if you have the infinite potential, then you take the difference in the slope is equal to this integral of the delta function. If it wasn't an infinite case, then it would have been the difference in the slope is 0. And so we still have that difference in the slope relation if we're doing the continuous waves. So we have the difference in the slope, take the derivative. So the derivative of the right side is these two. Derivative of the left side, those two. And we get this rather interesting looking equation for our second boundary condition. So this is an equation that relates A, B, F, and G. This is a relation that relates A, B, F, and G. That's 2 equations with 4 unknowns. Life is kind of hard in that case, right? So we need more conditions. And so the first thing we do is we say, we're going to define, A is representing a right-going wave on the left side, B, a left-going wave on the left side, and so on for F and G. And then we are going to arbitrarily say that we're starting with a wave of magnitude A coming in on the left-hand side. And so we have no wave coming in on the right-hand side, so there should be 0 for the left-going wave on the right-hand side. That's setting up the system. But it's not saying that has to be the case. That's saying for this specific situation, then what kind of scattering do we get? And so we're going to take everything and use A as kind of a normalization constant, if you will. It's going to be our reference. So what we're going to look for is what is B over A and what is F over A. B over A is going to represent what percentage is reflected. And F over A is going to represent what percentage is transmitted. And to find those values then, we put in what I specified for the definitions of, G is 0, and we can find what B is in terms of A and what F is in terms of A. And so we have this here is our reflection coefficient, and change color. And this here is our transmission coefficient. So those tell us the percentage that is transmitted or that is reflected for a wave that's passing over this well. So it's coming over this well. That well causes some of the wave to be reflected and some to continue on. And to make life easy to write, we define beta as m alpha over h bar squared k. Okay, so we stop there. So the actual reflection is taking the mod squared. That's the percentage that's reflected. The mod squared for the transmitted, percentage that's transmitted. Transmitted plus reflected needs to be 1. We'll stop here. Actually, that was the last slide anyway.
Do we need to know how to do?
You don't have to be able to do that second part. I'll probably have to X out some parts of the homework because I probably